Hello everyone, I'm Dr. Navneet Kaur, Associate Professor in Department of Electronics and Communication Engineering, Sagar Institute of Research and Technology College. Today I'm taking second lecture of subject Digital Signal Processing. In my first lecture, I had discussed about the concept of signal and signal processing. In that lecture, I had also discussed the advantages of digital signal processing. Now, in my second lecture, I'll be discussing about the basic concept of discrete time signals and the classification of discrete time signals. So I'll continue with my second lecture. Now, first, we will see what is a signal. I had discussed in my first lecture also that a signal is a quantity which conveys some information. Signals are represented as function of one or more independent variables, such as time, distance, position, temperature, pressure, etc. In our syllabus, we are considering signals which are function of variable time. Now, signals, they are of two types, continuous time signals and discrete time signals. Continuous time signals are practically signals which exist in nature. Whereas discrete time signals, they are obtained when we sample a continuous time signal. Discrete time signals can also be generated directly by some discrete time process. For example, if we want to measure temperature at an interval of say 1 hour, then the data which we get after performing an experiment of measuring a temperature will be discrete in nature. Like the temperature at say 10 a.m., then we'll have temperature at 11 a.m., then we will measure temperature at 12 noon, so on. So we will consider here the signal which is in the form of the temperature of the day, which will be discrete in nature. So here each data is having an interval of 1 hour between them. Now, in our syllabus, we have discrete time signals. So we will do discrete time signals in detail. Discrete time signal is a sample value of a typical signal or a sequence, and it is denoted by X bracket n, where n is always an integer. N can take value 0, 1, 2, 3, or -1, -2, -3, and so on. So we can say that Xn is defined only for integer values of n, and it is not defined for non-integers value of n. So we will have value of signal Xn at n is equal to 1, 2, but it will not have value at n is equal to 1.5 or 2.5. Discrete time signals, they are represented as X bracket n, where n will have value from -infinity to infinity, and n is compulsorily an integer. As I already discussed, that discrete time signal is obtained by sampling of the continuous time signal. So I can represent it as X and t, where t is the sampling period and n is an integer. Say if n is taking value 0, in that case, I'll get x0. That means it is the value of the signal at t is equal to 0. Now, if I'll take n is equal to 1, I'll get signal as xt. That means now I'm taking the value of the signal at time is equal to t. Now, if I'll take n is equal to 2, I'll get the value of the signal at x2t. That means now I'm taking the value of the signal at t is equal to 2t. Then it will be t is equal to 3t. Then t is equal to 4t. So here we'll observe two things. That the signal is only defined at 0, capital T, 2t, 3t, and so on. So here the interval between the two measurements is always same, which is equal to the sampling period. And the reciprocal of this sampling period is also known as sampling frequency or sampling rate. Now here, From this waveform, we can see the difference between the continuous signal and the discrete signal. This is the continuous time signal. Here we can see along the y-axis, we have an amplitude of the signal, whereas along x-axis, we have time. Now, this signal is having value at every instant of time, so it is continuous time signal. Now, if I'll do the sampling of this continuous time signal, I'll obtain the second signal, which is discrete in nature. Sampling means that I'll take out the samples of this signal at discrete instance, and the interval between the two samples is always uniform. So this interval is known as sampling period. Now, this is the graphical representation of the discrete time signal. Here we can see that along the x-axis, we have integer n, which is a function of time. Now, at n is equal to 0, we have value of the signal at n is equal to 0, so it is x at 0. Then at n is equal to 1, we have x at 1. Then n is equal to 2, it is x at 2. Then at n is equal to minus 1, we have x at minus 1, and so on. So here we can say that xn is defined only at discrete instance. It is not defined in between 0 and 1 or 1 and 2. It is only defined at n is equal to 0, 1, 2, minus 1, minus 2, and so on. Now, in this section, we will do the basic sequences or basic discrete time signals, which we generally use in the analysis of the digital signal processing. Now, first signal or sequence is unit sample sequence, which is also known as unit impulse sequence. Now, unit impulse sequence is represented by delta n. Delta n is always having value 1 when n is equal to 0, whereas it has value 0 when n is not equal to 0. Now, here we can see the graphical representation that when n is equal to 0, this signal is having value 1. Whereas at n is equal to 1, 2, 3, or minus 1, minus 2, minus 3, and so on, it is having value 0. Now, here we can say that any discrete time signal can be represented as a sum of weighted and shifted impulses. Weighted and shifted impulses means that here each impulse is scaled by some parameter and each impulse is a delayed impulse. Now, for example, we can understand this concept by using this signal. Now we can see that at n is equal to 0, the signal is having value 0. So there is no need of writing the signal at n is equal to 0. But at n is equal to 1, we can see that the signal is having value a1. Now I can write it as a1 delta n minus 1. That means a1 is multiplied by an impulse which is shifted at n is equal to 1. Now a1 and the value of the impulse is 1. a1 when multiplied by the impulse which is located at n is equal to 1, it will give a1 only. Now plus, now again we can see that n is equal to 0, we are having a value of signal a2. So I will write it as a2 into delta n minus 2. That means a2 is multiplied by the impulse function which is shifted at n is equal to 2. Now since this value of the impulse is 1, so a2 into 1 will give me a2 only. So now the next signal is having value at n is equal to 7. So I'll write a7 delta n minus 7. Now on negative side of n, we can see that we are having value at n is equal to minus 3, whereas the value at minus 1, minus 2, minus 4 is 0. So for this sample, we will write a minus 3 delta n plus 3, where delta n plus 3 represent an impulse which is shifted at n is equal to minus 3. So any arbitrary sequence can be represented as a sum of weighted and delayed impulses. So in general form, I can represent any sequence xn as summation xk delta n minus k, where k is having value from minus infinity to plus infinity. Now, the next sequence is the unit step sequence. Unit step sequence is having value 1 when n is greater than equal to 0, whereas it has value 0 when n is less than 0. So this is the graphical representation. Now, x-axis is showing variation of n. Now, when n is equal to 0, 1, 2, 3, and so on, the signal is having value 1. Whereas when n is having value -1, -2, -3, for all these negative values of n, the signal is having value 0. Now, this unit step sequence can also be shown as sum of the impulses which are located at n is equal to 0, n is equal to 1, n is equal to 2, and so on. So in general form, I can say that it is represented by summation k is equal to 0 to infinity delta n minus k. So delta n can also be shown as un minus 1. Un means the sequence which is shown in the graph, and un minus 1 means the sequence which is shifted by 1 unit to n is equal to 1. When we'll subtract un and un minus 1, we will get only one impulse which is located at n is equal to 0 and is having value 1. So it will give me the sequence delta n. Now, the next sequence is an exponential sequence, which is written as a alpha raised to power n, where a and alpha are real numbers. A is say positive and alpha is say having value 0 between 0 and 1. In that case, xn will also be positive, and since alpha is having value less than 1, so the value of the signal goes on decreasing as the value of n increases, which is shown in this representation. So as n goes on increasing, the value of the signal a alpha raised to power n goes on decreasing. Now, when alpha is having value between -1 and 0, in that case, xn will alternate in sign, but it will decrease in magnitude as n increases. And when alpha will be greater than 1, naturally this signal will show an increase in magnitude when n increases. So instead of this decaying exponential, in this case, we will have an exponential which will be growing. Now, next sequence is sinusoidal sequence. In general form, the sinusoidal sequence is represented by a cos omega naught n plus phi, where phi is a phase shift, omega naught is an angular frequency, and n is a parameter of time, which is always having an integer value. So here we can see that this is the discrete representation of a sinusoidal signal. So here if we'll join the envelope of this impulse, this discrete values, we will get a smooth sinusoidal waveform. So here there are the samples which are taken from the sinusoidal waveform, but it is discrete in nature because samples are taken at discrete instants of time. Now, we will consider the basic operations of the signals. Now, first operation is the addition operation, which is represented by this block plus. So here we can see xn is getting added with signal omega n, and we are getting yn. So yn is shown as xn plus omega n. Now, multiplication operation is represented by this triangle arrow. So xn, when multiplied by a, it gives yn. So yn is written as a into xn. Now, time shifting operation. Time shifting operation is given as yn is equal to xn minus capital N, where n is an integer. Now, if this n is taking a value greater than 0, we will say that it is a delay operation. Say capital N is equal to 1. So yn will be xn minus 1. So in that case, if I take n is equal to 0, y0 will be equal to x of minus 1. That means whatever the value of n is equal to -1 for x, it will having the same value for y at n is equal to 0. That means y is delayed by 1 instant with respect to x. So it is called delay operation. And in signal processing, delay operation is represented by a block Z inverse. So xn, when given to this delay block, it will give yn. So yn will be written as xn minus 1. Now, when n is less than 0, that means it is having, say, negative value. In that case, it will be an advanced operation. Say, for example, we will take capital N as -1. So, yn will be xn plus 1. If I'll take n is equal to 0, y0 will be equal to x of 1. That means y at 0 will have the same value what the signal x is having at 1, n is equal to 1. So yn is advanced by 1 unit with respect to signal xn. So xn, when given to this advanced unit, which is represented by block with z, it gives yn. So yn will be written as xn plus 1. Now, time reversal operation. Time reversal operation is represented by yn is equal to x of minus n. That means whatever the value at n is equal to 1 of y, that means if I'll say I'll put n is equal to 1, y1 is equal to x of minus 1. That means y at 1 will have the same value which x is having at n is equal to minus 1. Similarly, say I'll take n is equal to -1. So y of -1 is equal to x of 1. That means y will take at n is equal to -1 the value which x is having at n is equal to 1. That means here the signal is reversed with respect to y-axis. Signal becomes the mirror image of each other. That means yn will be the mirror image of the xn. Whatever the values of the signal at positive values of n, yn will have the same values at negative values of n. So this operation is known as folding operation or time reversal operation. Now, branching operation, which is used to provide multiple copies of the signals. Now, we will see the classification of sequence based on symmetry. Now, first is the symmetric sequence. Symmetric sequence means xn is equal to x of minus n. This means, say, if I am taking n is equal to 1, that means x of 1 is equal to x of minus 1. That means whatever the signal is taking value at n is equal to 1, it will take the same value which is having at n is equal to minus 1. That means the signal is symmetric with respect to n is equal to 0. Here in this graphical representation, we can see that the signal is having value n is equal to 1. It is same as the value at n is equal to minus 1. Then we have n is equal to 2. The value is same which is at n is equal to minus 2. Similarly, at n is equal to 3, the value is same which is at n is equal to minus 3. So this sequence is also known as even sequence. And the most common example of this even sequence is the cosine signal. Cosine signal is a symmetric sequence because whatever the value it takes on the right hand side of the y-axis, the same values occurs for the signal on the left side of the y-axis. Now next is the anti-symmetric sequence. Anti-symmetric sequence is represented by xn is equal to minus of x of minus n. Say I'll take n is equal to 1. Now x of 1 is equal to minus of x of minus 1. That means the value of the signal x at n is equal to 1 will be the negative of the value of the signal at n is equal to minus 1. Now here we can see in this signal representation that at n is equal to 1, the value of the signal is negative sign of the value of the signal at n is equal to minus 1. we can see that the magnitude of the signal at n is equal to 1 and n is equal to -1 is same, but the signs are opposite. So here it is negative sign, here it is positive. Now at n is equal to 2 and n is equal to -2, the magnitude of the signal is same, but the signs are opposite. At n is equal to 2, the signal is positive, whereas at n is equal to -2, the signal is negative. Whereas the magnitude is same in both the cases, n is equal to 2 and n is equal to -2. So this sequence is also known as an odd sequence. The best example of odd sequence is the sinusoidal sequence. So here we can see that the signal is anti-symmetric with respect to y-axis. Whatever the values the signal takes on the right-hand side of the y-axis, the magnitude will be same for the left-hand side of the y-axis, but the sign will be opposite. Now, the classification of signal based on the periodicity. Any sequence which satisfies the expression xn is equal to xn plus kn is called a periodic sequence. And this periodic sequence is having a period capital N, where n is a positive integer and k is any integer. The smallest value of the n which satisfies this expression is called the fundamental period. Now here in this signal representation, we can see that there is a periodic pattern which repeats after every fixed interval. Now here we have from 0 to 5. We have value of the signal 0, 2, 1.5, 1.50, then 6 at 0. Now this pattern of 7 samples, it repeats again. Now at 7 we have 0, at 8 n is equal to 8 we have 2, at n is equal to 9 1.5, then 1, then 0.5, then at n is equal to 12 we have 0, then at n is equal to 13 we have again 0. That means from 0 to 6 the pattern, it again repeats from 7 to 13. Then it will again repeat for, that means 0 to 6, that means 7 samples. The pattern is repeating for every 7 samples. So I'll say that this sequence is a periodic sequence with a fundamental period of capital N is equal to 7, because it is repeating after every 7 sample. This you can see for negative value of n also. Here this sample, this periodic pattern also repeats for every 7 samples. And the sequence which does not satisfy this periodicity condition is called a aperiodic or non-periodic sequence. The common used example of periodic sequence is a sinusoid waveform or complex exponential sequence. Now, as I already told, xn is equal to xn plus n for any periodic sequence. Now, as I discussed in my previous slide, that the complex exponential sequence is also a periodic sequence. Now, we will consider a condition which decides the periodicity of the signal. Now, if a complex exponential sequence is a periodic, it must satisfy an expression e to the power j omega naught n plus n, because here xn should be equal to xn plus n. So what I have done, I have taken n plus n in place of n. So if I separate these two exponential, e j omega naught n into e j omega naught n. Now, if I want that xn should be equal to xn plus n, for that this exponential should be 1. And we know that this exponential will be 1 only when omega naught n will be a multiple of 2 pi. So it will be written as 2k pi, where k is an integer. So for any signal to be periodic, omega naught should be written as 2k pi divided by n, where k is also integer, capital N is also integer. So I'll say that omega naught should be a rational multiple of 2 pi, because ratio of k and n, where both are integer, is a rational number. So omega naught should be a rational multiple of 2 pi. And in that case, the fundamental period of the signal will be given as 2k pi divided by omega naught. Now, the next classification is the energy and the power signal. The energy of any sequence is represented by summation n is equal to minus infinity to plus infinity and square of the magnitude of xn. Any infinite length sequence with finite sample values may or may not have a finite energy. But a finite length sequence with finite sample value is always having finite energy. Now, average power of any sequence is represented by limit k tends to infinity 1 upon 2k plus 1 summation n is equal to minus k to k. That means it is taking for period 2k plus 1 and square of the magnitude of xn. So we will define the energy of a sequence over a finite interval as same as the formula of the energy, but the limits are from n is equal to minus k to plus k. Now, the average power of an infinite length sequence may also be finite or infinite. An infinite energy signal with finite average power is called a power signal. That means a power signal is always having finite average power but infinite energy. The example of a power signal is a periodic sequence, which is always have finite average power but infinite energy. Whereas energy signal is a signal which is having finite energy but zero average power. The most common example is the non-periodic sequence. Non-periodic sequence are always energy signal because it is having a finite energy but zero average power. Now, thank you. This is all for today's lecture.